Good day, everyone, and welcome to our webinar presentation. My name is Adam Harris, Managing Director here of C-Therm Technologies. Very pleased to welcome you to our presentation today. We've been featuring different educational webinars throughout the past year, increasing the frequency of these since the pandemic really started, and we've been less able to travel to conferences and participate in different academic exhibitions and so forth. This has been a great way actually for us to really connect with a broader audience globally. We've been curating these webinars in different application areas related to thermal conductivity, and their popularity has continued to grow throughout the past year. We've delivered 39 of these sessions in the past year. I think we've had over 3,000 participants come through our webinar program. So it's certainly proving to be a popular offering, and I'm very pleased to be with you today and have you online with us. Today's topic is really looking at innovative, novel, next generation building materials, and specifically how we characterize the performance of those materials as it relates to the heat transfer, the thermal conductivity specifically. The webinar should run for approximately 60 minutes. We may go slightly over that. We do have a lot of content we're going to try to take us through. I'm providing the basic introduction. I'll speak a little bit to the background technology applied here and who C-Therm Technology is, but the real star of our show is Arya Hakimian. He's one of our application scientists at C-Therm, and he's the one that's really done the heavy lifting here in curating a variety of different application highlights, mostly taken from peer-reviewed publication featuring work done with the C-Therm technology for characterizing thermal conductivity in this area of building materials. We are recording today's session, so if you want to review any of this at a later date, you will automatically receive a link to the recording if you have registered for the webinar with your email address. Also, feel free to share that with any colleagues or folks that you think might be interested in the content. It's certainly freely accessible. We're happy to see that content shared. Just a few quick housekeeping items beyond that. This easy webinar platform, it does work best on Chrome. So if you do have any audio issues or you're seeing lags in the video, we do encourage you to switch to Chrome. It does seem to work a little bit more smoothly. And also just to note that there's a chat box there, and you'll see my colleague Rosa Chen. Rosa is one of our regional managers, for C-Therm Technologies, looking after China and other parts of Asia. But she does a great job helping us out with these webinars as well, helping moderate them, and she's behind the scenes, but she'll be there in the chat box and is a great resource. At different points in the webinar, she'll be dropping in links to other technical resources, materials, etc. So I want to thank Rosa as well for her help in putting this together. So we'll be getting started here. I'm going to launch into the formal presentation, and really I'll try to get through my part pretty quickly and get to Arya's content, which I think is the most interesting part for sure of the presentation. So a lot of folks register. This was one of our more popular webinars from the registration perspective. I see a lot of familiar faces and names, I'll say. I also see some folks that maybe aren't as familiar with C-Therm Technologies. So just a real quick little bit of background on who C-Therm Technologies is. We are a Canadian tech company founded about 15 years ago. And our reason for being, our raison d'etre in life, is all about thermal conductivity characterization. This is what we focus on explicitly, is in the advancement, the development, the innovation of thermal conductivity. Our goal is to make it easier to measure, to make it more accessible, to test under more representative conditions. And ultimately, we do that by focusing on the transient class of thermal conductivity characterization, which I'll talk a little bit more about as we proceed here. Just to give you a quick kind of overview of our product lineup, the two main products we would be featuring today, the one in the middle, the pyramid-shaped instrument, is called Trident. This was launched about a year and a half ago. Has become our most popular product to date. It's a research grade instrument. It's our most powerful instrument. It brings together the three most prominent methods for transient thermal conductivity: the C-Therm patented MTPS method, which is that stainless steel cylindrical type sensor you see to the lower right of the Trident system. The needle transient line source probe, that's the one in the middle there. That's great for polymer melts. It's our most robust sensor. It's sheathed in stainless steel, very, very robust. And then to the left of that, we have the TPS, transient plane source sensor. This is called our Flex TPS. It's a flexible sensor, so great for sandwiching in between concrete as an example. You'll see that featured in today's presentation. It's a really nice complement to the MTPS we have on the right there, which is the simplest and easiest sensor to use. It's a single-sided sensor. You'll see both of those featured very prominently in ARIA's content. To the left, we have our thermal conductivity kit, TC kit. Very low cost entry-level system. It does not meet the same ISO standard and other ASTM standards that Trident meets, but it's a great way to kind of get in the game, so to speak, and having a basic capability for thermal conductivity. It's often incorporated into experiential labs. It can be used there are some draft lab exercises that we offer as part of the product to incorporate into your teaching if you're in an academic environment. But it also makes for a great basic capability. This can test the conductivity of solids up to about 65 watts per meter Kelvin. Is great for groups that are, maybe a startup, bootstrapping a development. And also we're seeing a lot of interest in it also from folks that are maybe locked out of their labs or restricted from their labs and looking to establish a little bit more mobile capability, perhaps at home, at the home office, or other venues. But the TC kit's a nice addition to that lineup, just to kind of give you a range of capabilities for your available budget. Won't mention a lot on the TX system. That's really more oriented towards textiles, consumer goods. It's an instrument used for quantifying the cool feel or warm touch of different materials. So that can be a critical performance attribute in some applications, how something feels to the touch. There are a few applications for it in building materials. I don't think we cover it today, but it's, I know of work done in, I think it was Mexico, where they looked at working with the porosity of different ceramic tiles. Ceramic can feel cool to the feet when you walk on it, particularly in our northern climate in winter. So the researchers there were playing with the porosity structure of it to lower that thermal effusivity and by virtue of that, making the product feel warmer to the touch. And this can be quantified with this device. We have a feature webinar on this later this month if you're interested in that particular topic area. But really what you'll see is a lot of content here application-wise that relates to the use of Trident. And Trident is a very powerful product. It brings together the three most prominent methods for thermal conductivity. When we talk about having accurate thermal conductivity capability in your lab, unless you're testing the same type of identical sample, day after day, what you really want to look at is taking more of a toolbox approach. Because in thermal conductivity, there is no silver bullet that, one method that deals with all types of samples and environments and temperature ranges and so forth. So it's best to really have a versatile tool set that can offer you the best tool available for the job at hand. And Trident really brings together that with the MTPS, the needle, and the Flex TPS. Very complementary capabilities, as you'll see in progressing through some of the application content we'll be getting to here shortly. Our philosophy here is well represented in this quote we like to use in our presentations from Abraham Maslow. I know if you've seen me speak before, I often use this quote. I remember Maslow from my organizational behavior course in university. I wrote the hierarchy of needs, but this particular quote, I think really gets to the heart of the value proposition for Trident. And when all you have is a hammer, everything looks like a nail. And you often end up trying to use that tool, which can sometimes be damaging to your goal of achieving really, in this case, accurate thermal conductivity. So you have to be careful about your tool selection when you're measuring thermal conductivity. There are a wide range of different materials: solid, liquids, powders, pastes, conductive materials, insulative materials, and different environments you might want to test under: high pressure, high humidity, radiated environments in the nuclear sector. And it's really important to have a variety of tools so you can have a tool that's appropriate for the job at hand. And with this, Trident brings to those three different sensor types. This slide just gives you a good idea of what the relative sizes are of the sensor. And what we're identifying here is the active area of the sensor. So this would be the area that would need to be covered by the sample material. On the top, you've got the needle probe, which has an active length to it of 150 millimeters, and that gets immersed into the media which you're looking to test. This can be good for granular material if you're looking at soils or different granular geological material for site selection, perhaps for geothermal application. This can be a good tool for that particular type of application. We don't talk a lot about it in this content, but there are some interesting areas of applicability there related to soil testing. Also great for polymer melts and really sticky bonding materials that might damage the other sensors. It's our most robust sensor. The middle one is the Flex TPS, and that has multiple size sensors. So that's one thing to note, is with the Flex TPS, you do get that variety of sensor sizes. Depending on the heterogeneity, the homogeneity of the material, what the application is, your evaluated volume of material, you might have some important considerations there. You might want a larger evaluated volume of material, proportional to your measurement. So with the Flex TPS, you have a 6, 13, and 30 millimeter sensors provided as default with the Trident Flex TPS offering. So you get those 3 sensors in those sizes available with it. With MTPS, this is used in, I would say, 75% of the application area. So it is the most popular sensor. It's the most sensitive, has the best precision, reproducibility, and accuracy in most situations. Being a single-sided sensor, it's really easy to operate. It's factory calibrated, plug and play. It makes it just for a really simple user experience. You'll see this used a lot. You can, because it's single-sided, you can thermally map different areas of a composite. So if you do have some difference in performance, perhaps some settling in a composite that you'd like to investigate, the MTPS is a great tool for looking at some of those particular issues. These are some accessories available for the MTPS. So the top left, you see the powder test cell. Top right is the high pressure cell. We have a line of high pressure cells available for the MTPS. Lower left is the same cell that's used for powders, except in this case, it's being used for liquids. There is an O-ring that's on the bottom of that, makes it easy to test different liquids, very versatile. And then to the right is a great tool for dealing with any kind of compressible material. Something you want to think about if your material is compressible is that any densification of a material will typically impact its effective thermal conductivity. So if you think of, for example, an insulating batting material, when it's nice and lofted, you've got a lot of interstitial air present in that. Air, when it's not moving, is a great insulator. It's around 0.023 watts per meter Kelvin. So this is a great means of lowering the conductivity, improving the R value or insulation quality of a material. But you really want to make sure that you're testing that material with a representative level of compression. So depending on how compressed that material is going to be in the application, that's what you would want to represent and reproduce with the CTA pictured on the right. And that device just provides a really sensitive way of dialing that in reproducibly. It's a nicely designed compression test accessory. With TPS, Flex TPS, we have a variety of other accessories and options. The TPS sample clamp is used in a lot of testing. It's one of the ways we negate the impact of contact resistance with testing use with TPS. There's some great tech tips available on both MTPS and TPS. If you're interested in any of those tech tips on how to negate the impact of contact resistance, please enter in the chat box, and we'd be happy to follow up with you and providing you some of those documents. It is important that you have a good strategy, whatever your measurement is, MTPS, TPS, or others, on how you're going to negate the impact of contact resistance. The higher the thermal conductivity of the material, the more impactful the contact resistance is. So one of the strategies here is to apply compressive force with the TPS sensor, and that's what the TPS sample clamp is for. You see those different size sensors available in the top right. These sensors are also available in higher temperature formats, which you see in the lower left. We have TPS sensors up to 500 degrees C. I think this particular one you see pictured is 300 degrees C. And then to the lower right is the powder cell for use with the TPS as well. Also with TPS, there are some specialty utilities. And one of the things I really love about the Flex TPS method is it is a little bit more complicated to use. It requires a greater training on the user's part. So if you want simplicity, I would point you more towards MTPS. That's great for quality control applications, for reproducibility amongst labs, rather. But if you're getting into some more advanced areas of thermal conductivity, TPS really unlocks some, very strong capabilities with the utilities available with that. SLAB is for testing typically higher conductivity material, which are most often more in sheet format. So you can think of like a copper sheet or a slab of material, hence the name, the slab. The anisotropy utility is for use for oriented samples that have different heat flow patterns. So you can look at the radial and axial difference in heat transfer from a thermal conductivity perspective with the anisotropy TPS utility. And then thin films. So thin films are a very strong area of application for TPS. There's a capability here to test films in the range of under 5 watt per meter Kelvin. The thin films is a broad area. I want to be careful in managing expectations there a bit. It's not for all thin films. There are thin films that are higher conductivity, for example, than 5 watts per meter Kelvin, where this would not be recommended for, but it does provide a very strong capability for below 5 watts per meter Kelvin. So a little bit of detail there. There's a lot of information being presented here, and what we're trying to educate and advocate within this kind of space on is the pros and cons of these different techniques and methods. And so all the methods are good. They all have their merits. They all have their limitations as well. And what we really try to focus on is speaking and informing the audience on what those capabilities and limitations are. What are the particular applications where we recommend certain types of sensors and certain types of solutions? This is all codified in the method selection guide that was produced a couple of years ago by folks from our team and external experts in thermal analysis. It's a comprehensive document. It's about 50 pages. And what it really does is explains thermal conductivity methods, as well as not just the transient methods that we're focusing on today, but also including steady state techniques, such as guided hot plate, and techniques that are most suitable for really high temperature ranges, like laser flash. If you've got to test at 1,000 degrees Celsius, then laser flash is a great solution for that. But laser flash brings a lot of other requirements along with it, including the need for heat capacity, the thermal expansion of the material, etc. So it's really important to understand the points of, theory that support the method, and what are the practical limitations of it when you go to measure different types of materials. Lots of methods can be adapted for different scenarios, but it doesn't mean that they're necessarily optimal for testing these different types of materials. So the method selection guide is available as a free downloadable resource. I think Rosa will probably drop that in as a link here. Yeah, there she is. And if you'd like to download that, please feel free. It's a great free resource available. I also want to just mention, I'm going to transition this over to Ari in just one or two more slides, but we've got a couple of cooperation partners that are a really strong part of what we do. We work closely with a couple of French organizations that are leaders in their respective fields. Metrovib is a world leader in dynamic mechanical analysis. We've got a webinar next week on innovations in crack growth, fatigue testing with DMA. If you're interested, that's a really strong webinar where we'll have a subject matter expert on the line with us from Metrovib. And we also work closely with C-Therm instrumentation. That's a part of our technologies group. They're world leaders in thermal analysis, DSC, TGA, et cetera, calorimetry, have really high temperature capabilities, really high sensitivity capabilities. We work closely and represent them in the Canadian market, and with Metrovib represent them in Canada and the US, but some really great partners that we're proud to work with. We are the best in the world at thermal conductivity, and these organizations are the best in the world at what they do. And so, you know, we also find you're judged with the company you keep, and we like the company we're keeping with Metrovib and C-Therm. They're excellent companies. I'll end just on a note in terms of customer experience with C-Therm. There is a page dedicated to client testimonials. I think it's got over 50 different testimonials on it. This is one that we often use just because the organization is really well known, NASA. Just talking about purchasing a C-Therm thermal conductivity instrument after seeing a demonstration of how fast and easy it is to operate. This is from Dr. Enrique Jackson at NASA. I remember when we could still travel, visiting with him and testing some powders, and that was one of the things that was really interesting to him, was testing powders and liquids. But you know, a nice summary there from Dr. Jackson in terms of satisfaction with the purchase. Gave us a 10 out of 10, extremely satisfied, which is exactly what you hope to hear. We work really hard. We've invested multiple millions of dollars in the development of the product over multiple years and launching Trident, and I'm really proud of what we've accomplished with introducing that to the market a year and a half ago, and certainly that seems to be reflected in a number of the comments we're receiving. This is another comment from a researcher in the UK, Haydale Composites, Stuart Sykes, and I just mentioned this one because I think it's really interesting from the perspective of what he's doing with the instrument and thermally mapping different composites, filled composites that have different additives in there, nanomaterials. When you're working with composites, one of the big concerns is the dispersion and the uniformity of that dispersion in the polymer matrix. And one of the things that you can uniquely do with our technology, particularly the MTPS single-sided sensor, is map different location areas of a sample material. So it makes for some really unique insight, rather than just averaging the full thermal conductivity performance, to see if there are localized differences in performance, and be able to have both a macro sense of the performance of that composite, but also a more localized view of, okay, is it consistent from side to side, from location to location? Do you have a settling effect, and so forth, and how that can help inform your product development moving forward. Okay, with that said, I'm going to stop sharing my deck here and invite Arya Hakimian up. Arya is our application scientist here at C-Therm. If you've been on a demo with us in the last year, Arya's also headed up the demo facility. So he works closely with clients and helping them understand what's the best sensor to select for different types of application areas. If you'd like to book, I'm just going to put in a quick plug here for it. If you'd like to book a video demo with Arya and the team, these can be organized. They can be as short as 30 minutes, or they can be an hour plus, depending on how much you're looking to cover in that content. But there is a form that you can sign up for if you'd like to have a more in-depth video demonstration of the product. But with that said, I want to introduce Arya, who's on screen with me now. And Arya, I'll invite you to go from here. I'll rejoin you at the end for the closing discussion.
Awesome. Thanks, Adam. Hey, everyone. So as has already been mentioned, we'll be going over some more technical related aspects of testing some of these materials that are involved in buildings and construction. Now, as we go throughout here, one of the main reasons why we're looking at this is you can relate it to how the material performance will affect the overall influence on the quality and efficiency of the build. One of the main driving factors behind a lot of these innovations is obviously related to the cost of heating and maintaining ideal living temperatures inside of these buildings and houses. You can see just from this example here, the sheer amount of energy that's required to maintain heating, whether that's the inside, your water, air conditioning. It's an extremely large amount of our resources, which translates to billions of dollars on a yearly basis to perform and maintain this cost. When we take a closer look at some of these materials and components of a build, there's some definitely key areas where heat is lost or gained, and this can have more of an influencing factor depending on the time of year. Obviously, in the summertime, you want to keep the cold air in, and in the wintertime, you want to keep the cold air out. But you can see just some examples here. One of the main areas for heat loss in buildings is the ceiling or the roof. As you can imagine, because the heat rises, a lot of that heat is going to be traveling upwards into the structure and therefore lost out of the top. On the other side there, one of the main areas where heat is gained is through windows. Obviously, the sun and the light coming in from the exterior. This is one way where heat can start to build up, and again, very, very relevant depending on the area, the climate that you're in, and the season. Here we just see an IR image of a building. Obviously, noticing that there are quite a range of hot spots and cold spots throughout. This is related to obviously the different areas of the building, height-wise, what the material that the building component is made out of, whether it's a structural, thicker material, a window. Buildings encompass quite a wide range of materials and components, so there's a lot of factors to consider here. But all of this is going to be coming back and relating to thermal conductivity. This is what we're going to be exclusively focusing on during our presentation here today. Obviously, there's a lot of aspects to an ideal building material that need to be considered, whether that's the structural, mechanical properties of that sample, how efficient that material is. Cost is obviously a big factor, but with respect to efficiency and the temperature maintenance capabilities, this is where we're going to draw thermal conductivity information from. So just breaking it down here, for those who may not be familiar, thermal conductivity can be seen as essentially the amount of thermal energy, so watts, traveling through a given material thickness, so meters across a temperature gradient K. So thermal conductivity can be reported in watts per meter Kelvin, and this is what we will be essentially going over and discussing today. So as I mentioned earlier, buildings can encompass quite a range of just structural components and different material types. Whether it's residential, industrial buildings, they all carry a similar overall format. Obviously, you have your base. These can include different types of foundations or slabs. There's the structural backbone or the skeleton, so whether that's made out of metal beams or wood, and depending on the type of building. And then you have your exterior, the extremities, so the roofing, the walls, flooring. Inside of all that, there's insulation. So a lot of different components to consider here, and again, a wide range of materials. You can have porous concretes, you can have dense metals, woods, ceramic, polymers. Really, building materials are a very hard application space to kind of group into one little box. they incorporate quite a range of material types. And because of that, the focus that we'll be looking at in the coming slides are a lot of different case highlights and applications, looking at how thermal conductivity is being used to help improve or quantify the effect that is for the different material components and structural aspects of the buildings. So with that, we'll start jumping into some specific case highlights. And first off, we will be looking at some studies that involved using the modified transient plane source, or MTPS sensor, for the thermal characterization. Maybe touching on it just a little bit of what Adam had said earlier, but the MTPS, it is the single-sided sensor, really easiest to operate and use, offers some of the widest versatility with respects to the samples you can test: high conductivity, low conductivity, solids, liquids, powders, pastes. Really incorporates a vast range of samples. And the other thing, and this can be really influential for the building materials as well, is taking a look at being able to test in those representative conditions, whether the building or the environment that the structure is in, whether it's a warm climate, cool climate, underground, above ground. These can all be factors that should be considered. And when you're going to test the thermal performance of those materials, really being able to mimic those conditions is going to be crucial to getting the best overall understanding of how that material will end up performing in its end use scenario. So starting out, we have a study that was done on thermal parameters of roofing slates from the Czech Republic. So in this study, we'll take a look at researchers that were aiming to investigate the effect of different natural mineral sources as roofing slates, or the material that's incorporated in the roofs. You can see on the right there the areas where the minerals were extracted from. So obviously different locations, different mineral compositions will all lead to different thermal performances. And this study, the researchers were interested in examining both in-plane and through-plane thermal properties, as well as seeing how the overall parameters were influenced by the effect of temperature. Some more notes from the study that was done. The mineral composition for each thing that would be referenced is measured by XRD, but the thermal properties were all measured using C-Therm's MTPS sensor. So you can see here from the thermal conductivity results, they noted both the parallel or in-plane and perpendicular through-plane directions. And across all the various mineral sources that were taken, we did see, generally speaking, the parallel or the in-plane did result in a higher thermal conductivity measurement compared to that through-plane direction. Now, obviously, this is specific to the subsection of mineral materials that they were looking at, but it is interesting, and something worth noting is that some materials can have significantly different thermal properties and thermal performance is in different directions. So this can have bearing on how you're aligning the materials during the construction, how they're incorporated into the materials, if it's an additive. All of this can come into play when evaluating the overall material performance. Next, as I mentioned, they were also looking at how those samples fared under the influence of varying temperature. And we can see from the graph, I mean, there's an overall trend here. Generally, the thermal conductivity increased as a function of increasing temperature, and this is common for this class of rock material. But obviously, this does have some bearing on the end-use application. So whether the roofs were in a shaded area exposed to the open sun, in non-shaded areas, these different materials can have different performances based on the temperature that you're subjecting them to, which will in turn influence their insulative performance as a roofing material. Up next, This study, an experimental study on the thermal performance of phase change materials and wood plastic composites for building roofs. So again, we're looking at an application for roofing materials, but this study is, we're kind of touching on some of that next generation advancements in these classical building materials, incorporating the use of a phase change material. So you may have seen phase change materials mentioned if you've ever seen talks on thermal management in batteries, various technological devices. But we're seeing here phase change materials being included in things for building the materials as well. So in this study, they were aiming to add the PCM to the composite for their roofing applications. And the reason behind this is the phase change material will generally improve the temperature stability of a system when the thermal input is delivered to that sample that contains the PCM. That material will undergo what's known as a phase change, obviously related to the name, changing from either solid to liquid or liquid to solid, depending on the direction of that temperature gradient. And this can act almost as a buffer in enabling the stability or the temperature change for the overall material. Now, thermal conductivity data from this study was actually used by the group for some computational simulations that they were looking to do. This is another big area where you can do some initial testing of the various materials, get your input parameters, and then instead of going and actually needing to build an entire structure and do the in situ testing, taking that data and running some of these computational simulations is a way to get around going all the way to that end product, and can really be used to tailor and fine tune your parameters before moving on. So they had some material measurements with the MTPS, others were just reference values directly inputted, but you can see there's different materials that were incorporated in their study, some concrete, insulation, and then the different polymer-based phase change materials, all seeing quite a range of different thermal conductivities. And this is what they were using for inputting into their simulation study. And what they're aiming to do is influence or see the influence of the material with and without the phase change material and with different phase change materials on how well it would be able to handle a direct input of solar radiation or essentially the delivery of that thermal input. So we can see in general here, the overall temperature rise in the sample as a response to that radiation was generally seen to be higher in the samples that contained no PCM, and overall were somewhat lower with the various PCMs added. And again, this is what we would expect to see. The PCM is coming in there as a stability device, aiming to reduce the overall increase that was observed in the wood plastic composite. With that, they're able to do some studies on the overall energy consumption that would have been used. Again, kind of tying back to one of the main purposes behind some of these studies, coming back to the energy consumption and the cost of living to maintain. Overall, what they were able to show is without the PCM, generally energy consumption was higher. There were some few divergences from that trend, but generally speaking, across the data set, it was noted that the introduction of a PCM did have a beneficial result on not only the stability and the temperature increase, but the overall energy consumption that was used. Up next, this is taking a little pivot away from roofing materials, but taking a look more so at the introduction of a silica aerogel used as thermal insulation coating. So the introduction of aerogel materials has been something seen throughout a few different sectors as well. The ability of an aerogel as an insulating or reducing agent that is able to block the transfer of heat is something that's built up in popularity over the last few years, and we've started to see that across a broad range of applications. So in this study in particular, they were noting heat loss in the winter and gain in the summer can be significant. And again, coming back to one of those first slides, especially in those rooftop materials, but also in walls, various structural components of a building. Heat loss is something that will affect different components differently, but it is there regardless. So they were aiming to add an insulative or this porous material to the building in hopes to reduce the overall thermal conductivity of the build and therefore increase the insulative performance. In this study as well, really important that they understood the thermal performance as a function of temperature. And they were also examining, again, these materials using the MTPS, but we can see some of the SEM images that they were taking to view the structural aspects of their coating on the right here. So we can see that the aerogel coating added this layer on top of the substrate that they were looking to measure. Ultimately, what they were able to show is compared to just the pure binder material without the incorporation of any aerogel, it had the highest thermal conductivity at room temperature. And through the addition of a 1-to-1 and then a 1-to-4 ratio of binder to aerogel, they were able to show an overall net decrease in the effective measurement for the thermal conductivity. Now, on top of that, when investigating the influence of temperature, again, this trend held true across the different temperature points of interest. As we can see, the sample noted with the dark blue squares had the higher concentration of the aerogel material and overall the lowest thermal conductivity measurement compared to the other material. So this is an example of how you can incorporate some of these materials into the overall build to either in this case, decrease the effective measurement. Next up, looking at a preparation of energy-efficient paraffinic PCMs, expanded vermiculite and perlite composites for energy saving in buildings. So in this study, they're using they had the understanding that the PCM was going to improve the overall thermal performance, improving the stability of that material, but they were investigating instead now the matrix that the PCM was added to and how that can actually come into combination with the introduction of the PCM and how that can play off each other and indicate which materials may be better suited as the overall building structure when you're looking to add some of these materials on top. So in this study, they were adding the PCM to two different matrices, as mentioned, so a perlite and vermiculite samples. Both of those materials were used in a structural transformation and they can undergo various modifications that are temperature dependent. So subjecting them to various temperature conditions can result in different effects related to not only the stability of the material, but in this case, how much they would expand by. So their main goal was influencing the influence of the PCM on the surrounding matrix. The way they actually added the PCM, this is just a quick little diagram here of how this was done, but it was through a vacuum impregnation setup. Basically, the PCM was added to that sample through this vacuum setup here. So the material was coated and loaded into the various samples. Overall, what they aim to do is, one, quantify the thermal performance of just the PCM on the far left here, and then see how that overall thermal conductivity response changed when you introduce that PCM into the matrix of that material. So we see in the middle into the perlite sample and on the far right in the vermiculite. So the PCM in both cases having the same conductivity, but the overall thermal response did change based on what sample that material was added to. So this can kind of give you an idea that if you are looking to add or modify any of your base samples or base materials, it's important to, one, understand what the additive is going to do, but also how it's going to interact and play off the base material that you're looking to use in the first place. Up next, taking a look at thermal and acoustic insulation boards from a microalgae biomass. Now in this this application here and the one following, one thing with building materials too is obviously you're looking for high efficient materials, structurally stable, but there is an application and the field of adding eco-friendly, or you can view them green chemistry approaches to improving the thermal performance or the efficiency of those materials, but in an environmentally friendly way. So this is something that's, again, popped up across multiple sectors. And again, we'll take a look at some of those applications here in the building material space. So in this study, one of the main reasons and for the group's investigation of this is these foam boards were traditionally made from petroleum-based materials. Obviously, petroleum is a massive industry, and a lot of those byproducts are used for a lot of our common, plastics and different types of samples and materials that are used in an everyday life. Obviously, these researchers are aiming to use a more eco-friendly approach to get the same quality insulation from these boards, and they were investigating a few different sources. So first is a polybeta hydroxybutyrate, or PHB source. This is a bacteria-derived material, highly biodegradable, renewable, so it has that eco-friendly aspect to it. Next was a spirulina biomass. Again, this is a microalgae-based material, similarly highly biodegradable and renewable. And then something a little more traditional, which is a glass wool. So what they actually did, they took those 3 different materials and created different samples with different mix ratios. So obviously, again, the glass wool, PHB, and spirulina. And they were aiming to assess the overall thermal performance based on the different compositions to see which would be the best overall performing. So the samples A, B, C, and D on the far left, we can see, generally speaking, very low thermal conductivity response. Sample B did result in the lowest overall measurement. Therefore, that was the sample combination that was best suited for their study. But then they also compared it to some other traditional materials and also other bio-based additive samples. So, as an example, concrete coconut mixtures, different plaster, wheat fibers, natural wood shavings. A lot of these additives that we're seeing in this list here are things that are either waste products or simply discarded through the process of their build. So you can imagine cultivating various fruits and vegetables. A lot of the skins, the fibers, things that aren't edible would simply just be discarded and tossed off to the side. This adds to your waste cost. But if there's a way to recycle those, bring them into other processes and add them in different materials, not only are you saving on overall cost, but it can be a more eco-friendly alternative with similar performance if you're able to control those parameters properly. And this last one here, comparative study on different biomass from olive grove in the manufacturing of sustainable ceramic lightweight bricks. So in this study, the researchers were aiming to add a material to their brick compound. Bricks have been used for a very, very long time in building material in these types of applications. The idea here is by adding this additive, one, it's going to reduce the overall amount of that pure material you need to build the brick, but by incorporating that recycled sample, it should, one, be an eco-friendly alternative, and as well as decrease your overall cost. So they were looking to study the influence of different materials for both their thermal and acoustic behavior. So the biomass that was used in this case is various olive waste products. So there's the pruning, wood, and leaf. So these 3 different materials, all from the same overall olive sample, were used as different filler materials. So they not only investigated the 3 different materials, but also studied the effect of adding them in different fill ratios. So the the brick material with the filler was mixed, compressed, and then fired, and this is how you got the overall sample was made. And then through the study of the thermal conductivity, they were able to hone in on the best performing thermal sample. So this was obtained with a 15% loading. And they were found that related to the ideal pore size that was generated during the firing process of that brick. But even though that 15% loading resulted in the best overall thermal performance, when taking in other considerations such as the physical and the acoustic properties of that sample, the overall best performing sample was the 7.5% additive. So this is a scenario where even though one sample did result in the best overall thermal response, structurally and through some other properties considerations, it wasn't the overall best choice. So it's again, thermal conductivity is one aspect, and it's a very important aspect that needs to be studied. But there are other properties and characteristics that need to be taken into consideration when looking at the overall picture. So that was a lot on the MTPS, and again, kind of highlighting the fact that it does cover quite a range of materials. Up next, I have a few slides looking at some applications and highlights using the Flex TPS, or the transient plane source. Again, just to kind of freshen the mind there, the TPS, it is that double-sided sensor. It is a flexible sensor. It is a little bit more, what we say for advanced users, it requires a little bit more understanding of how to adequately set up your test. You have to manually set your timing, power parameters, and things like this. But ultimately, it is a great option for some materials as it does not require a contact agent. And this is what we'll be highlighting here in these coming slides, as well as it does conform to the ISO standard, so ISO 22007. So one of the main ones, and the first one we'll highlight, is the application of concretes and cements. So with any type of hygroscopic material, so something that will absorb water, this is best tested via TPS. So the MTPS sensor, certain materials such as polymer, ceramic, metal-based materials will require the use of a contact agent. And in the case where those are compatible with the overall sample type, this is where the TPS comes in to provide that complementary aspect to your testing needs. Again, here when we're looking at cements being relatively heavy and very rough samples, the flexible sensor design mitigates any potential risk to the sensor. And while it is a slightly more advanced method to operate, it's still vastly superior in the respect to the versatility and speed compared to some of those other steady state methods that may be available. So this is just a quick example. We can show that measuring this cement across 10 measurements, we get a very nice tight measurement spread. Average thermal conductivity coming out to about 0.52 watts per meter Kelvin. But really this is an example here of the material type that you're looking to test really being most appropriate for the TPS sensor. And this last highlight here, so this was some testing that was done internally on some foamed glass gravel from a company called Glavel. Now this type of sample here, it really represents one of those innovative materials in that next generation that is being seen in building applications. The sample, it's a lightweight, highly durable and thermally insulative material that can be used in various aspects of building, whether it's for a sub-slab, backfill, rooftop fill applications. The structural stability of this sample, along with its lightweight, really add for some really interesting properties that can be accommodated in quite a few application spaces. Again, here, derived from a recycled glass, has that eco-friendly aspect, chemical hazard material free. And as a note, they are beginning manufacturing in their Vermont location this coming summer. So for anyone in North America, this is something that can be obtained relatively locally. So we can kind of see some example usage here. Typically, these sub-slab applications require the use of a filled cement or other materials, but this very lightweight material can simply be added in and compacted down to create that bed. On the right image here, we can see it can be used as a filler material where it's eco-friendly. There's no harm to the environment or risk to the surrounding structural aspects of the base. So again, just a really nice option there that can be added in for these different application types. So this sample, like I said, is really tested best via the TPS method, related to the fact that it is a porous material that would have otherwise absorbed the contact agent for MTPS. So really great option for TPS. We can see here 3 repeat measurements coming in an average reported value of about 0.07 watts per meter Kelvin. Again, indicating a really nice insulative material. And again, look at what the added aspect of being lightweight and durable really makes it a great option for these building materials. So that comes to the end of some of the case highlights we wanted to touch on today. Did just want to mention we do have some upcoming webinars, as Adam had alluded to earlier. Next Thursday, February 18th, Innovations in Crack Growth Testing with DMA. And then the following week, February 25th, looking at quantifying touch performance via our TX platform, so measuring that cool touch, warm feel of a fabric. So I see Rosa just posted in the chat there. If you are interested in kind of joining any of those, feel free, and we'll be happy to see you next time. So with that, I just want to say thank you for joining our session here today, and I'll throw it back to Adam for the Q&A session.
Excellent. Thank you very much, Arya. A wonderful job as always. Covered a lot of different application areas. You can see a real diversity of materials represented in those different user cases, and how the different methods complement each other in dealing with those scenarios. So wonderful job, and thank you again for curating a great presentation on some novel building materials and speaking specifically to the performance characterization of thermal conductivity. At this point, I want to thank everyone very much for listening in. We're going to stop the recording portion. So if you're reviewing this file as a recording, we want to say certainly thank you for the interest. We will proceed to a Q&A here. Just before we close the recording part, though, I did just want to mention that if what you've heard so far is interesting and you're trying to map out your options for thermal conductivity, is the time of year where often we're looking at some budgetary numbers in terms of our CapEx. If you'd like a quick quote, there's a tool we'll make available to facilitate getting you some quick estimates in terms of investment costs for Trident. It is a modular system, so there's a little bit of a discussion that we typically have just in terms of your needs in terms of different materials you'd be looking to test, temperature range, etc. But I see Rosa's just entered the quick quote link, and so just wanted to offer that if anyone's interested in having a peek at what that looks like. We're certainly happy to facilitate that. There's no pressure from our side. It's just if that's something that makes sense from your view. Okay, so with that said, I'm going to stop the recording